This presentation is titled Data-Driven Hydrology Education, Using SELDM to Enhance Student Understanding of Stochastic Modeling and Stormwater Management. I'm Lillian Jeznach, an Associate Professor of Engineering at Roger Williams University in Bristol, Rhode Island, and I also hold an appointment of Faculty Hydrologist at the U.S. Geological Survey at the New England Water Science Center in Northborough, Massachusetts. This is a recorded presentation of what was presented at the Association for Environmental Engineering and Science Professors, AEESP, Research and Education Conference that was held on May 20 to 22nd, 2025, hosted by the North Carolina Consortium of Universities at Duke University's campus in Durham, North Carolina. State DOTs are increasingly subject to total maximum daily load, or TMDL, requirements for water quality improvements that are implemented through the National Pollutant Discharge Elimination System, NPDES permits. As a result, state DOTs may incur significant costs to construct, operate, maintain, and monitor performance of best management practices and other stormwater treatment facilities that treat stormwater from sources outside of the right-of-way, as well as stormwater from roadway sources. Practitioners need tools to assess the impervious area loading contributions to catchments and the effects of management actions on receiving water concentrations. And they may be interested in questions such as, do downstream loads meet the total maximum daily load? Do downstream concentrations exceed a water quality threshold? How much does the particular site of interest contribute to the TMDL relative to other constituent sources? What's the probability that a structural BMP will decrease downstream loads or concentrations? If you have multiple sites, which site should I focus my efforts and resources on? And how do I estimate the impacts if I don't have any data for my site? Civil and environmental engineering graduates need to be prepared to enter the field of hydrology with knowledge of effective tools and methodologies used by practitioners to evaluate the impacts of impervious area runoff on catchments and receiving water bodies. And so this was the goal of this two-day workshop. The workshop was developed to introduce students to a model widely used by state DOTs through a two-day workshop to support learning stormwater management concepts with a practical application. SELDM is the model that was used for the workshop, and it is the Stochastic Empirical Loading and Dilution model developed by the USGS in cooperation with the Federal Highway Administration. SELDM is a stochastic model because it uses Monte Carlo methods to create a sample of events representing combinations of flows, loads, and concentrations. It's an empirical model because it's based on data and statistics rather than pure theory. And it's a loading model because it provides storm and annual loads, and a dilution model because it calculates the mixing of upstream and highway runoff to indicate the chance of exceeding a target concentration value. The workshop was developed based on existing training materials for DOTs that have been previously developed. SELDM has been widely used and tested by the USGS, the US EPA, the U.S. Fish and Wildlife Service, and other state agencies. It is therefore a useful tool that can be used in the classroom to both enhance student understanding of stochastic modeling and stormwater management, and also a practical tool for students to gain some more experience in prior to entering the workforce. This tool was collaboratively developed by the USGS and the Federal Highway Administration. It's a valuable resource to state DOT practitioners interested in assessing highway loading contributions to a catchment and the effect of management actions on receiving water concentrations. SELDM is designed to facilitate the National Environmental Policy Act process. More specifically, it's designed to help answer the question, is there a significant impact? And if the initial answer is unknown, SELDM can be used to help refine initial estimates as part of the environmental assessment process. SELDM uses a simple mass balance approach to calculate flows, concentrations, and loads by storm and by year. It uses Monte Carlo methods to generate precipitation, pre-storm flow, and runoff coefficients to generate the storm flows. It generates concentrations as random variables, dependent variables, or for the upstream basin as transport curves, which are relations between stream flow and concentration. It has a BMP module that generates performance criteria, including flow reduction, hydrograph extension, and concentration reduction. However, some BMPs can increase flows and concentrations during some storms. Downstream flows, concentrations, and loads are calculated from the upstream values. This diagram shows the components of upstream flows and highway runoff flows that combine to define the downstream flow statistics. The physiographic and anthropogenic basin properties affect the upstream pre-storm flow and the storm flows from the upstream basin and the highway site. The latitude and longitude of the drainage area are used to identify stream flows used to define the pre-storm flow volumes. The total impervious fraction is used to calculate the runoff coefficient statistics. The basin length, slope, and basin development factor are used to calculate the timing of runoff from the upstream basin and the highway site. SELDM supports the environmental decision-making process because it is preloaded with precipitation, streamflow, and water quality data, and it has regression equations relating basin properties to hydraulic variables that control the volume and timing of runoff. This facilitates rapid development of robust planning level estimates that can be refined with data and statistics from nearby sites, or if the situation is critical, with data collected at the site of interest. If you use regional values with site characteristics, you can assess conditions at many sites in a day. If you need to collect defensible data at a site of interest, this will cause substantial delays and cost increases that will be orders of magnitude greater than the initial modeling effort. A Level 1 analysis requires regional inputs from the same ecoregions and rain zones based on hydrologic similarity. A Level 2 analysis uses data from nearby hydrologically similar sites. A Level 3 analysis uses user-defined statistics from data collected on the site of interest, which is the most expensive and time-consuming kind of analysis. For our class exercise, we did an example Level 2 analysis. To bridge the gap between academic learning and practical application, a 2-day workshop was developed to introduce upper-level undergraduate hydrology students to SELDM. The workshop aimed to enhance student understanding of stochastic modeling and equip them with skills to interpret model outputs for water management decisions. Similar workshops have been developed for DOT practitioners, and this workshop was a simplified version of those. The specific learning outcomes were 1. To reinforce hydrology concepts such as precipitation, watersheds, hydrographs, stormwater runoff, stormwater controls with the application of SELDM. Second was to apply SELDM to generate planning level estimates of upstream impervious area and downstream hydrographs and water quality constituents. Third was to apply SELDM to generate planning level estimates of stormwater structural controls on a downstream hydrograph and water quality constituents. And finally, to interpret data outputs from SELDM by producing graphs that can be used for water management decisions. Day 1 included model background, model inputs, and running the model. And then day 2 included interpreting model outputs. The workshop target audience is upper-level undergraduate students in an engineering hydrology course or similar. This exercise would be appropriate to incorporate towards the end of a course after students have encountered and learned these concepts. To do this workshop, students are expected to be familiar with drainage area definition and characteristics such as area, length, slope, and imperviousness, basic mass balance concepts, precipitation concepts such as regional differences, storm volume, or storm duration, streamflow hydrograph concepts such as how it's measured, the shape, and the effects of land use and land cover, runoff concepts such as runoff coefficients and the effects of land use and land cover. Students should also have a basic understanding of statistics, so they should understand the average, median, standard deviation, skew, and probability of exceedance or non-exceedance concepts. And they should also have a basic understanding of what a structural BMP is, including different types, flow reduction concepts, hydrograph extension, and water quality treatment concepts. The case study application for this workshop was a Level 2 analysis of Howard Brook, a 1.34 square mile basin in Northborough, Massachusetts. The exercise focused on modeling the effects of stormwater runoff and the impact of stormwater best management practices, or BMPs, on downstream conditions. Students engaged in model setup, running simulations, and analyzing results using graphical and written communication methods. Students were given the following information about the watershed and the impervious area site of interest. They were given the highway site information, how much area, length, slope, and total impervious area. And then they were given similar information about the upstream watershed, the area, the flow path length, the slope, and the total impervious area. The workshop guides students through the data input steps laid out in the model GUI and walks them through the steps in a worksheet. This takes place on day 1 of the workshop. First, students document the project analyst, the project description, and the project analysis description. Next, students enter in the statistics for the site and region, the hydrology, and finally water quality and the BMP, if it is included. Then they run the analysis. The students receive background on each of these steps in a presentation as they fill out their worksheet and enter the model information. I'll discuss the steps briefly in the following slides. The latitude and longitude are the geographic basin properties, which are used to specify much of the hydrologic data used in the analysis. The latitude and longitude are used to automatically select regional precipitation, streamflow, and water quality data that are preloaded in the SELDM model. This is a map of the United States showing a hypothetical location at a latitude of 40 degrees and longitude of minus 90 degrees. This map shows the U.S. Environmental Protection Agency rain zones as the black bordered and numbered polygons. The rain zone can be used to select precipitation statistics. This map also shows a discretized version of the U.S. Environmental Protection Agency Level 3 ecoregions as colored areas on the map. The ecoregion can be used to select precipitation, streamflow, and water quality statistics in SELDM. The drainage area, basin length, and mean basin slopes are physiographic properties for the highway site and the upstream basin. And then the total impervious area is used to define the volume and timing of storm flow from the highway and upstream basin. You can select precipitation statistics by region or by using more than 2,610 NOAA hourly precipitation data stations with at least 25 years of data preloaded into SELDM. The latitude and longitude of the precipitation data stations are used to rank the stations by proximity to the site of interest. SELDM uses the EPA definition of a runoff generating event, which is based on hourly precipitation values, a minimum precipitation value of 0.1 inches, and a minimum inter-event period of 6 hours between events. You can select streamflow statistics by region or by using data from more than 2,784 USGS long-term stream gauges preloaded into SELDM. The latitude and longitude of the stream gauges are used to rank the stream gauges by proximity to the site of interest. The population of pre-storm flows is represented by a complete population of daily mean stream flows, which we get from stream gauges. The selected statistical distribution, log Pearson type 3, is used for generating stochastic estimates of pre-storm stream flow using the frequency factor method. The total impervious area is defined as the proportion or percent of contributing area occupied by anthropogenic impervious surfaces, which primarily consist of pavement and roofs. Total impervious area can be expressed as the fraction from 0 to 1 or the percentage, 0 to 100, of the total drainage area. SELDM uses the impervious fraction to define the total impervious area of the highway site and the upstream basin. The runoff coefficient is the ratio of runoff to precipitation for each storm event. During each precipitation event, some water is absorbed, some fills surface depressions, some evaporates, and some infiltrates. The remaining water runs off into natural or man-made channels, which drain to the receiving stream. SELDM simulates highway runoff water quality statistics using data from the Highway Runoff database. This index map shows highway runoff monitoring stations in the United States from the Highway Runoff Database version 1.0, Federal Highway Administration and State DOT data sets, and the additional Highway Runoff Database version 1.1 dataset. Highway runoff quality is simulated as a random variable using the average, standard deviation, and skew of highway runoff water quality values. SELDM simulates upstream water quality statistics using paired streamflow and water quality data. This is a map showing the ecoregions and the location of 24,581 USGS surface water quality monitoring sites with paired streamflow and water quality measurements. These measurements include 24 constituents commonly studied in highway and urban runoff studies. Water quality transport curves were developed by ecoregion for sediment, total phosphorus, and total hardness, and random water quality statistics were developed by ecoregion for pH. Lastly, SELDM uses the triangular hydrograph to simulate the timing of the downstream hydrograph. SELDM uses a black box approach to model the net effect of one or more BMPs at a site of interest because there are so many complexities, data for characterizing detailed processes is lacking, and there is a great uncertainty in the application of data from site to site and from storm to storm. With the black box approach, we are given the flows, concentrations, and loads from the source area and use transfer functions to calculate the flows, concentrations, and loads to the receiving waters. In SELDM, these transfer functions are the ratios of outflows to inflows with rank correlation to inflow values. On the second day of the workshop, students use a spreadsheet template to analyze and interpret the model results. One example question students can explore is, what's the risk of exceeding downstream water quality thresholds? In the class example, students compare their phosphorus results to two common limits for phosphorus. The common limit for running waters is 0.1 milligrams per liter, and the EPA recommended limit for ecoregion 59, which is where the example site is located, is 0.02375 milligrams per liter. The results indicate there is about a 40 to 50% probability in exceeding the common limit for running water upstream and downstream, regardless of the highway runoff or BMP. There is approximately a 90% probability in exceeding the EPA limit upstream or downstream. SELDM also provides a population of total annual loads or yields because the storm events are aggregated into load accounting years. This figure is an example of annual yield results that could answer the question, how much does a BMP decrease the annual yields from an impervious site? The graph shows a simulated population of 30 yearly values. Note that the x-axis is similar to the previous slide and that it shows the percentage of years that equal or exceed a given value on the y-axis. Based on these annual yields, we can determine the long-term average values, which is advantageous in the development of total maximum daily loads, or TMDLs, which is another implementation of SELDM. The stochastic analysis shows the information that could be used to assess variability and estimate a margin of safety. An assessment of student learning pre- and post-workshop revealed improved understanding of core hydrology concepts, for example, precipitation, watersheds, hydrographs, and stormwater runoff, as well as an increased familiarity with SELDM as a tool for modeling the effects of runoff and BMPs. Additionally, students gained confidence in estimating the effects of stormwater controls and interpreting model results to inform water management strategies. Overall, the workshop effectively introduced students to SELDM and provided them with practical skills to apply statistical models in hydrology. The workshop materials include detailed instructor notes, model installation instructions, 2 presentations on model background and setup, step-by-step worksheets with solutions, and pre- and post-assessments. These workshop resources are suitable for upper-level undergraduate civil and environmental engineering courses in hydrology or related courses. By integrating this exercise into the curriculum, educators can better prepare students for careers in water resource management, enabling them to leverage advanced modeling tools to address complex challenges in stormwater management and environmental engineering. With that, I'd like to thank the USGS, the New England Water Science Center, in particular Elena Spatzel, a supervisory hydrologist of the Integrated Modeling section, for her support in this work, and also the Federal Highway Administration, in particular Gregory Granado, who is a national stormwater specialist and was the SELDM model developer and the developer of many of the workshops used for the DOTs that this particular workshop was based on. These are the links to the USGS SELDM project page and also to the workshop materials, both of which are free for download. We hope you'll take advantage of these materials for your educational use. Thank you.